Hello, in the last lecture we talked a bit about intermolecular forces, and now we're going to talk about the consequences of intermolecular forces. So here are the consequences. So viscosity. Viscosity means resistance to flow, capillary action, and surface tension. So let's start with viscosity. There's a saying, maybe you've heard of it, it's not very applicable here, but slow as molasses in January. Maybe you've heard of that before. Molasses, it's very thick, syrupy stuff, even thicker than syrup. Well, maple syrup is pretty thin, but it's very viscous. So, and generally speaking, when things cool off, they become more viscous. So, molasses, so really thick syrup, is very slow when it's cold in January. So it flows very slow. Resistance to flow, that's from viscosity. So that means that molasses, and when it's cold, is going to have much resistance to flow versus something like water. And what does that resistance to the flow come from? It comes from the intermolecular forces. This is big business. There is a whole section of research called flow assurance, and that's done by petroleum companies. So when you get oil from the ground, for instance, there's lots of things that can go wrong. And there's a whole branch of research on this. So if you want to make money, that's something you can go into. Capillary action, and shown there with a capillary tube. Well, we have our heart in our chest and it's pumping, but we have blood that has to get to our fingertips. And even as I'm moving my hand outside of the range of the camera, the blood's still going to my tip of my fingers. And what are those tiny blood vessels called that leave the arteries? They're called capillaries. So how our part of our circulatory system works is because there's a little bit of attractiveness between blood and our blood vessels, and that allows the blood to be drawn away from the arteries. And the arteries get smaller as they leave the heart, go into the smaller parts of the body, into the capillaries, and that's also what helps draw the blood. So that way our hearts don't have to work as hard to get the blood to those various areas of the body. Now, mind you, the heart is a very strong muscle, but it takes some of the pressure off of that by having the capillary action. Now, it's a moderation argument because the capillaries can't be too strong, or the attractiveness between the blood vessels and the blood can't be too strong, then the blood would never move. So, and also surface tension. So there's a couple things with surface tension. Surface tension tends to make liquids spherical. So I've kind of drawn here that the meniscus of water here. If you ever pour water on the ground, you don't tend not to look at it, but it actually beads up a little bit. If you pour mercury on the ground, it beads up even more. And one of my favorite movies of all time is Terminator 2, where Arnold, the "Hasta la vista, baby," shoots the T-1000 and the liquid there. That was done with mercury. So if you wonder how they did that special effect, well, at least the melting part and the joining back together. And if you look at mercury in this test tube, it has a very high surface tension. Water has a slightly lower, but it also can be drawn up the test tube. That's called the meniscus. Why is it drawn up a test tube and a meniscus? It's because glass has hydroxide. So glass is mostly just, long story short, it's melted sand, melted silica, and there's hydroxyl groups, AOH groups on all of the on the surface of glass, and attracts the hydrogen bond there, attracts water up the sides of the container. If you use plastic glassware, like in lab, I have online lab kits for my chemistry and society classes. Those do not have meniscuses because it's not made of glass. Also, there's these, I try to draw, this is my insect. See, I'm a chemist, I have limited artistic ability. There's these insects in the mainland, they go in streams, we call them water striders. They can walk on water. And their 6 legs, and the water kind of has like a lip in it where they stick their legs, and they move around. So this spherical nature of things, so like BBs, the copper BBs that you shoot from BB guns, the way that you make BBs is you just pour molten copper, and when you pour the copper, it turns into a sphere just naturally by its intermolecular forces, and it forms the almost perfect spherical round shape. Sometimes they just pour them in air, sometimes they pour them into water. So it's the process to make BBs is not that difficult, just plain old intermolecular forces. Okay, and vaporization. We'll talk a little bit more about vapor pressure eventually, but we did talk about it a little bit last semester. Vapor pressure, it's as if, so if you have a liquid, it's as if the liquid is putting pressure. We model it as the liquid is putting pressure on the surface. That's not really accurate. What it is, it has to do with the distribution of thermal energy. So at so temperature is distribution. So temperature means average kinetic energy. So at a higher temperature, there's a more broad distribution, and a low temperature is a more narrow distribution. And shown here in this chart. So if you look at this chart, we have on the y-axis the fraction of molecules, and the x-axis the kinetic energy of each molecule. And the average, so remember the temperature, we did this last semester by, at least in gases, with the root mean squared velocity. So you can see that the red curve on the right has a higher root mean squared velocity than the blue chart, the blue line on the left. And but you also notice that the lower temperature, the blue line on the left, has a smaller fraction of this line here, this minimum energy needed to, and this is the energy that's needed to break the intermolecular forces of the liquid. And then a higher temperature, you're going to have a higher fraction, and that's really where the vapor pressure comes from. And then the boiling point of a liquid is when the vapor pressure reaches the ambient temperature. So, or the vapor pressure reaches the ambient pressure, excuse me. So, but it takes energy to break the bond. So evaporation is an endothermic process. And you know that in part if you ever put rubbing alcohol on your skin. So water, and this is also sometimes referred to as the latent heat. So the latent heat for water is relatively high at 40.7 kilojoules per mole. So to give you an example, and this goes both ways. It takes a lot of energy to boil water, but it also takes a lot of energy. A lot of energy is released when water condenses. So if you've ever gone to saunas or steam room, you can sit in the sauna for a while and like start getting hot. You go into a steam room, you're in there, at least, I mean, I'm in there for 30 seconds and I'm feeling really hot and I'm colored like a lobster because I'm very fair-skinned. I get pink very easily. So that's because the steam is condensing, and as it condenses, it releases the latent heat, the 40.7 kilojoules per mole. That's why steam feels so hot. And also, when you put like rubbing alcohol on your skin and then it evaporates, it feels so cool, is because it's taking that latent heat away from your body. And also, when if you ever put out a campfire with water, what do you hear? You hear making steam. It's putting out the fire by taking the heat away by turning water into steam. That's how water puts out fires. Okay, so use this in calculations. What is the mass in water or grams that can be vaporized at the boiling point with 155 kilojoules of heat? And this is just good old dimensional analysis. So 155 kilojoules. So, and we're going to divide by the latent heat. Well, water, 40.7 kilojoules. And then once the mass, water is 18 grams. And you can see the units cancel. And I might actually just do this. I probably would pause it, but I think I'll just, it's a pretty easy calculation. I'll just throw it in my calculator. 155 divided by 40.7 times 18, and we get 68.6 grams of water. So that's how much water, 155 kilojoules could evaporate. Okay, so now these are common mistakes that I see with students. So many times I want you to go through your calculator with me on this to make sure you get the right answer. And the most common mistakes I see are order of operations. So the first thing you do for order of operations is what's in a parentheses first, then powers and logs, then multiplication, division, then addition and subtraction, and the rules go left to right. So for instance, 6, 3, and 2, it depends on which one you do. So 6 times 3 plus 2, and I am using my smartphone as my calculator. It's a smartphone, but it's dumb. It can only do what I tell it to. It can't solve problems. It's us as humans. It's our job to put the input in machines. So when you put them in the calculator, you'll get different results depending on what order of operations you use. Okay, so this is your turn. If you want, you can pause the video and try this out. If not, I will go ahead and solve this for you. So first thing first, how much heat is required to vaporize 100 grams of acetone? So we have to get the molecular weight of acetone first. Let's see, 3 carbons, 6 hydrogen, 1 oxygen. So 3 carbons, that's 36 plus 6 for that, plus oxygen is 16. So 36 plus 6, 42. That's 48 grams per mole. No, it's not. I'm sorry. It's 58. 58 grams per mole. And so how much heat required? 100 grams of acetone. 100 grams times mole to 58 grams times 29.1 kilojoules per mole. And this is an easy one. I'm going to put it in my calculator. Oh, and it's 54. Sorry. 54 grams per mole. 3 times 12 is 36. Okay. 100 divided by 54. I should be careful about doing math on the fly. Alright, so this is... I might have screwed this up. How do you pause? It turns out I should not have doubted myself. It was 58. So, and this is 50.2. So, that is how you solve that. Okay. And so maybe you've heard this joke before. Someone who is sick and laid up saying, well, gee, you've been sick, you've been laying here in bed all day, looks like you haven't been doing much. You can reply, well, it may look like that, but on a molecular level, I'm teeming with activity. So that is what's happening in equilibrium. We'll talk more about equilibrium later on in the semester, but boiling a liquid is what's known as a dynamic equilibrium. So if you look at here, you have a vessel, a closed system where you have a liquid, in this case water, and so if you initially start off with no water in the vapor phase, water will be released in the vapor phase, but it's dynamic because some water is evaporating, some water is condensing, so the water is still moving back and forth. Same thing even within the bubble of a boiling liquid, there's still a dynamic equilibrium going on there, even within the bubbling of a heating liquid. So when you look at a boiling thing of water, a vessel of water, it's actually a lot of things are going on. It's not just all leaving the system. There is also going to be water condensing back in the liquid phase. And water also, I mentioned that the boiling point of water changes with respect to the ambient pressure, so that the vapor pressure, when the vapor pressure equals the ambient pressure, the liquid boils. And here at various locations, you can see the boiling point of water will decrease. I guess I got to charge up my pencil. Okay, so if you look here, for instance, in Denver, Mile High City, the boiling point of water is 94 degrees. And maybe you've seen somewhere, like in cookbooks, they'll say if you're simmering something, you have to add an additional 20 minutes to simmering. Why does that happen? Well, bacteria tends to be killed at 165 degrees Fahrenheit. And if you, in any phase change, so boiling water is equilibrium, which means it's 100 degrees. So it doesn't matter how fast you boil something. The walls of the container can get above 100 degrees, but the liquid itself cannot get above 100 degrees. So that means in Denver, well, it's 100 degrees here at sea level. Well, I'm in Wailuku, Maui right now, so I'm about, I don't know, 500 feet above sea level, which is essentially sea level. But Denver, Colorado, the boiling point of water is going to be about 94 degrees Celsius. So you'll need to cook food. If you're cooking it in like a crock pot with simmering water, you have to cook it a little bit longer. The oven, it's the same temperature, same time. Or like a deep fat fryer, it's not going to matter. But if you're using water, sometimes you have to cook things a little longer. Okay, so next thing I'm going to do is talk about the Clausius-Clapeyron equation. So pay attention to some of this. You'll see the forms that we're going to use are going to be used over and over again throughout this class. And this is also known as a semi-empirical model. So you'll see lots of semi-empirical models in this class and other classes too. So there's derived models. So the ideal gas law, that's a derived model. So that's the ideal gas that doesn't exist, that has no attraction for itself, that has no volume but exerts a pressure. So that's a fantasy. There's no such thing as an ideal gas. So what's another thing people can do is they can take a bunch of data and they can run a bunch of experiments and find out that those data make sense if you apply this model over a certain range. And that's what Mr. Clausius and Clapeyron did, and they collaborated and they formed the Clausius-Clapeyron equation. Another example, if you've taken physics, friction. Friction is a semi-empirical model. So if you look at the friction between my hands rubbing together, there is friction there. And if you study it, they'll talk about the normal force times the coefficient of static friction. That's a semi-empirical model. That's something called a lumped sum approximation. It takes all the variables and throws it into one variable, and it's really just kind of a fudge factor. What is the friction really? The friction is the attractive force. It's electrostatic. It's the attractive force between each of the atoms in my hand with the other atoms in the hand and in the other hand, and then that causes a resistance to motion. And you have to do that for each atom in my hand and sum it up for the other atoms in each of the hand, or whatever surfaces you're seeing rubbing up against each other. And if it moves a little bit, it changes everything. So you have to recalculate it. Or you could just do a lump sum approximation, find out, well, you know what, rubber and concrete tends to have this much, so we can kind of use this model to work over this series of parameters. And hey, if it's ice, it's this. If it's asphalt, it's this. Then we'll design our tires using that. That's a semi-empirical model. It's just we do a lot of things to make it work, especially if you go into engineering. Engineering has loads of these, loads and loads of these semi-empirical models, and they work over different ranges. So we are not we're guilty of using them too in chemistry, and here's an example of one, the Clausius-Clapeyron equation. So what they found out is that if they plotted a bunch of data of vapor pressure, of the natural log of vapor pressure versus the inverse temperature in Kelvin, the natural log of the vapor pressure in millimeters of mercury. This is important. You have to use millimeters of mercury. If you use atmospheres, if you use any other units, if you use PSI, it won't work. This model only works for these units, for millimeters of mercury and inverse temperature in kelvins. If you do that, looks like a very linear relationship, and then every line has a slope and has a y-intercept, and the y-intercept is the natural log of beta term that they coined there. How do you get rid of that term? You can take two of those points and you can subtract them, and you can get rid of the natural log beta. So the 2-point form there is written. So the natural log of the vapor pressure of the second one over the first is equal to minus the heat of vaporization over the gas constant R times the quantity of 1 over T2 minus 1 over T1. And there's a couple things I want to talk to you about. So natural log rules. So here are some two natural log rules. Natural log of A minus natural log of B is the same thing as natural log of A over B. Natural log of A plus natural log of B is the natural log of A times B. And what are natural logs? If you take e to the natural log of whatever value, it spits that out. So the natural log is the opposite of the exponent function. And let me show you the derivation, like blue, for this. So we have ln P2 equals minus delta H over R 1 over T2 plus natural log of beta. ln P1 equals minus delta H over R 1 over T1 plus natural log of beta. Let's subtract these two. We get natural log P2 minus natural log of P1 equals minus delta H over R 1 over T2 minus 1 over T1. Natural log beta terms go away. And ln P2 minus ln P1 is ln P2 over P1 as we get in that equation there. So if you're wondering how you get that, that's how you derive that. Okay, well let's use this. Methanol has a normal boiling point at 64.6 degrees and a heat of vaporization of 35.2. What is the vapor pressure of methanol at 12 degrees Celsius? So we're going to use this equation here. And the first question is, what is the normal boiling point? Normal boiling point, it's at 1 atmosphere, or 760 millimeters of mercury. That's what a normal boiling point is. So which you just have to do is to pick which one you want as P2. I think I'll choose this as P2, and I'll call this one. So that'll be our P2, our unknown, and so this is our T2, and that means then. Change this color. This will be our temperature. So this is going to be our P1 and T1. So first of all, turn these to Kelvin. So 12 degrees Celsius. 12 plus 273.2. This is 285.2 Kelvin and 64.6. 64.6. That's 273.2. This is 337.8. Okay, so we're going to change those to Kelvin. And I like to do all the math first. So I'm going to take e to both sides, and I'll get P2 over P1 equals e to the minus delta H vaporization over R 1 over T2 minus 1 over T1. Okay, and then I can then multiply both sides by P1, and I just get the pressure, the vapor pressure of the second is equal to the vapor pressure of the first times the quantity e to the minus delta H over R T2 minus T1. Now I just put in the numbers. So putting in the numbers, our second vapor pressure at 12 degrees Celsius is the vapor pressure of the first, 760 times e to the minus delta H vaporization, so minus 35200. So that's kilojoules. I always write out the joules, and R is 8.314 joules per mole Kelvin. So I guess just kilojoules per mole. So times the quantity 1 over T2, 1 over 285.2 minus 1 over 337.8. Now, okay, before I put in these numbers in the calculator, let me look at these numbers and see if they make sense. So I start with the fractions 1 over 285 versus 1 over 337. I think about that number, and that's going to be a positive number. I subtract those two. So because 1 over 285, that's a bigger number than 1 over 337. So like, what's a bigger number, 1/2 or 1/10? 1/2 is, right? Because the smaller number on the denominator makes a bigger number overall. So the 1 over 285 minus 1 over 337, that's going to be a positive number, which makes the entire thing negative because it's e to the minus. So that e to the negative number, that's going to mean that I'm going to have a number. This whole number is going to be less than 760. So 760 is going to be multiplied by a small fraction. And but that makes sense, that as we cool something off, so if something has vapor pressure at 760 at 64.6 degrees Celsius at a lower temperature, we expect it to be lower. So, and the numbers that we put in should suggest that, so the last thing we have to do is put those numbers in the calculator. So let's go ahead and do that. And I like to do it once because that way I don't mess it up. 35200 divided by 8.314 times the quantity 1 divided by 285.2 minus 1 divided by 337.8, close parentheses, close parentheses. Okay. Oh, I see what the problem is. I forgot the negative sign. Insert negative sign. Okay. Okay, I just went and calculated that there and took a picture. So look what I put in there for it. So the 760 and times the exponent e to the minus delta h, and I know it's in kilojoules. I always write it out because I forget. Divided by r, and then multiplying. So remember, it goes left to right. So taking the negative 35,000 divided by 8.314 times, then that still works. If I put parentheses around the divisor between r and that, then it would divide by the quantity. But that works there with the fewest keystrokes, and we get 75. So then the answer is P2 is 75.3. And this is, the units are millimeters of mercury with the semi-empirical model. So, and the other thing to note, this is an estimation. It's not real. Okay, and just to tell you a little bit more about logs and powers. So if you are confused on how this works, so our number system is base 10. So if you look here, anything raised to the 0 power, except for 0 or infinity, is 1. So anything raised to the 0 power is 1. Like I said, except for 0 or infinity. Anything raised to the first power itself, so squared power, so 10 squared is 10 times 10. 10 cubed is 10 times 10 times 10, and so on. And negative exponents, that's 1 over the whatever item is. So like 10 to the minus 2 is 1 over 10 squared. A logarithm is the opposite of an exponent. So if you look at, say, the log of, and we say log, we usually mean log base 10. Log base 10 of 100 is 2, because 100 is 10 squared, and we're looking for that exponent. And log of 0.01 is minus 2, because that's what 10 to the negative 2 is what 0.01 is. Now you can change the base. For instance, the log base 7 of 49, 49 is 7 squared, so log base 7 of 49 is 2. It's the opposite. It's the opposite of that, raising that power. A natural log is log based e, and e is the Euler's number. And I'm using this for very easy numbers to show you, but if you look at log 5, for instance, here, if you do the inverse log, take 10 to the log 5, you get 5 back out. There's a little bit of error there, but it's just because the calculator is taking all those digits out. So, but if you do it exactly 10 to the log base 5, log base 10 of 5 is 5. And same thing with the natural log. So the natural log, if you spit it out, well, the natural log can do the opposite of the exponent function. Okay, so this is your turn. Why don't you try solving this one? So heat of vaporization of water is 40.7. Vapor pressure water is, what is vapor pressure water at 25 degrees Celsius? Same thing. So why don't you try and solve this on your own? Okay, so if you try it on your own, this is how you solve it. It should be 27.9 torr, or millimeters of mercury. Millimeters of mercury is same thing as torr. And so that is the answer for this. Although the real answer, so if you actually measure the vapor pressure in the laboratory, the answer is 23.8. I'm not doing this just to mess with you. The point of this is that it's a model, so a semi-empirical model. There is errors associated with having a model. So when you get a model there, you will not always get the real answer. I'm not saying like if this was a problem, a test, the answer would be 27.9. But the point of this is that whenever you model something, there's going to be a little bit of error associated with that. And the part of the error, that's just what we have to manage. We have to manage that error by using our models, using our experiments, using what we know when we do science. So that's all for this section. Oh, and if you're having a hard time with these natural logs, so solving for the natural logs, doing the math, putting the number in your calculator, this is when you should make an appointment to come see me, like in face-to-face, or we can talk to a tutor, because this is very important. You're going to be using this through this entire class. So if you're finding you're getting stuck now is the time to remediate this. Okay, so let me know if you're having any issues on this, and it'll save both of us some work later on. Goodbye for now.